Okay, so since I was asked to talk about host galaxies, I'm actually not going to tell you about this super fascinating parent stability candidate that Robert just mentioned, but it will be on the archive tonight, so look out for it. I am going to tell you about host galaxies of type 1 and type 2 superluminous supernovae, but as with Robert's talk, it's actually going to be mostly type 1s. So let me first remind you, why do we actually care about the host galaxies to begin with? Of course, the goal here is we want to know what kinds of stars explode as superluminous supernovae. And it would be wonderful if we had an event that was really nearby and we could just go look at some, pre-explosion imaging from HST or something and just look at the star that exploded. This is 87A, the most extreme example, I guess. But of course, because the rates are very low, pretty much all superluminous supernovae that have been detected and likely will be detected are just way too distant for any kind of direct progenitor detection. So what we do instead is we study their host galaxy properties as a proxy for the stellar population to get some handle on the progenitor population. And just to remind you what these main models are and what kind of progenitors they would require, as Robert was just talking about, one possibility, at least for some superluminous supernovae, are these pair instability supernovae, in which case we would require a very massive progenitor. The exact mass range would depend a little bit on model and metallicity, etc., but we're in the mass range of initial masses of more than 100 solar masses for sure. In addition, you probably want low metallicity in your progenitor, or stellar winds are gonna mean you lose so much mass that you don't manage to build up a sufficiently massive core, basically. Now, there are models out now that can make pair instability supernovae from non-zero metallicity models, but we're still in a low metallicity regime. Similarly, for circumstellar interaction models, just observationally, from the kind of CSM masses that we observe, which are often in the tens of solar mass range, you need a massive progenitor. In addition, you have the problem of how do I shed tens of solar masses in a few years prior to exploding. The kind of models we have for that, for example, the pulsational pair instabilities, is something that also requires a massive progenitor. So both of these first two progenitor models, you are in the very massive star regime. Now, for the magnetar, which is this third model, the main thing you need actually is a star that is spinning at sort of millisecond spins for your newborn neutron star. So you require high angular momentum in the core, but you do not necessarily require an extremely massive star. So the kind of ejecta masses that you derive when you fit these magnetar models to superluminous supernovae are maybe a factor of 2 higher than normal 1C supernovae, but you don't necessarily require a 100 solar mass star. So this is a new enough field that I can basically make this a historical review talk and just sort of walk you through the discoveries as we made them. So from the very beginning, and even just from the fact that we never discovered a superluminous supernova in a targeted galaxy survey, you might already guess that there's something weird going on with the host galaxies. And indeed, as you look at some of these early detections of superluminous supernovae, a stunning number of them had no detected host galaxies at all to begin with. So on the left side here, you see a figure from Robert Quimby's 2011 Nature paper. So the right-hand column shows all of these supernovae from PTF, and in the left-hand column you see the pre-explosion images, or the Sloan images actually, and there are no galaxies there detected in Sloan. Well, sure, you might say, okay, SDSS is not that deep, whatever, so there's probably some dwarf galaxies there. Then there was also this mystery object, SCP-06F6, that was discovered to be a superluminous supernova eventually. That was actually serendipitously discovered in an HST survey, and even in the HST pre-explosion images, there was no host galaxy detected. So that's just telling you, from the beginning, before we even were able to study the galaxies, we kind of knew they were probably pretty faint. Here's another way of showing that. So this is the earliest host galaxy study that was done by Don Neal et al. In 2011. So this is a color magnitude galaxy diagram. Basically, they used data from Galax and Sloan to look for all of these host galaxies of the then known superluminous supernovae. So you have the UV minus R-band color on the y-axis and the host magnitude on the x-axis. And the two things you should notice here, first of all, again, a lot of these are actually non-detections. They're upper limits, and they all sort of cluster in this blue and faint corner, with some notable exceptions that I'll come back to. Later, we were also able to study a couple of host galaxies in detail. These are the first few of that. So supernova 2010 GX and PS1 10 BZJ. Now, I'm showing here a spectrum of 2010 GX on the side here, and at least for the galaxy people in the audience, you'll probably notice this is a pretty unusual galaxy spectrum. First of all, the emission lines are very strong. Oxygen 3 here is booming. This equivalent width is huge. You actually detect the auroral oxygen 3 4363 line, which is in itself an indicator of very low metallicity. And also just from zooming on this H-alpha nitrogen 2 region, there's basically no nitrogen 2 here, which is also telling you, in this case, the host galaxy is a very low metallicity galaxy. And the host galaxy of PS1 10 BZJ is similarly extreme. It also has booming oxygen 3 emission. It's at redshift 0.6, and we still detect this auroral oxygen line, which is really unusual. And I'm showing on the right side here just a fit to the spectral energy distribution, which allows you to derive things like the stellar mass and age of the galaxy. In this case, the best fit stellar population age is something like 5 million years. So this is a very booming starbursting galaxy. So certainly from the early objects we were able to study, you get the idea that these are pretty extreme host populations. But of course, now that we've discovered tens of superluminous supernovae, we can start to look at samples. So these are the main studies I'm going to be talking about. In terms of where the supernovae themselves were detected, they sort of fall into three groups. So there's a number of examples from these various public surveys, like the Texas Supernova Search, Catalina, La Silla Quest, Pesto has classified a bunch, etc. Both type 1s and type 2s have been found. These are in general mostly at low redshift, with some exceptions, like Dark Energy Survey, for example, are finding them at high redshift now. My own work has focused a lot on the Pan-STARRS Medium Deep Survey, which generally found type 1s and mostly at high redshifts. So this sample spans redshift 0.5 to 1.6. And then also recently, PTF came out with their host galaxy samples. So Dan Purley has a very nice poster advertising those results, and I'll be talking about some of those as well. So what have we learned from looking at all of these large samples of superluminous supernova host galaxies? I'm going to start by talking about the type 1s, because I think they are the most interesting. So the first thing I want you to take away is overwhelmingly type 1 superluminous supernovae prefer dwarf galaxy hosts. So what I'm plotting here on the left side is galaxy luminosity, just versus redshift. So this is from my compilation paper that uses data both from Pan-STARRS and the then public objects. And so the black points here are the superluminous supernovae, and in comparison, the blue points are the Goods core collapse supernova sample, so core collapse supernovae in a similar redshift range, and the red points are long GRBs. And then on the right side, you're seeing the same data just plotted as a distribution. And you can see overwhelmingly, this black line is way to the left. Superluminous supernovae, at least of type 1, come from a different galaxy population as do ordinary core collapse supernovae. And this is really interesting because it's telling us that whatever you need to make a superluminous supernova, you need more than just ordinary star formation, or you would not expect this result. Another thing to notice in this plot is that a lot of this big difference is driven by the low redshift objects. So there are some hints of a trend with redshift in this plot, where most of the very extreme galaxies we see are at low redshifts. This could be perhaps due to a metallicity effect. I'll come back to this. So if you compare just the Pan-STARRS sample, which is the high redshift and dashed line here, they are more consistent with the others, but still more extreme. Here's a similar plot just showing, again, galaxy stellar mass. Same thing, scatter plot here, distributions here. And again, you see the superluminous supernovae host galaxies are totally inconsistent with the core collapse host galaxies. The median stellar mass is a few times 10 to the 8 solar masses. And again, they seem to be perhaps even more extreme than gamma ray burst host galaxies, so I'll get back to that as well. Now, since masses and metallicities are generally correlated, you should not be surprised to see that they also are generally found in low metallicity galaxies. So this is a plot from Yorgos Leluda's compilation, just putting them on a mass metallicity diagram. So all of these blue points are the type 1 superluminous supernovae, and you see they indeed cluster in this low mass, low metallicity corner. So we have, let's see, we have low masses, we have low metallicities. We also have at least an excess of galaxies with high specific star formation rates. So I'm not going to claim that every type 1 superluminous supernova explodes in a high specific star formation rate galaxy, because you do have this tail down here. But compared to core collapse supernovae, you see a lot of them in high specific star formation rate galaxies. That's also shown in this plot just on the right, showing stellar mass versus specific star formation rate. There's a lot of them up in this corner. And much more so than, for example, SDSS galaxies. Now, this sort of preference for, or potential preference for high specific star formation rate manifests in a couple of different ways. So a number of these superluminous supernova host galaxies are what, if you're a galaxy person, you would classify as an extreme emission line galaxy. That is to say, the spectrum is dominated by these very strong emission lines. That is plotted here on the right, and just plotting straight out the equivalent width of the oxygen 3 5007 line. And you know, SDSS is this gray line way over here in this plot, and this blue line is the type 1 superluminous supernovae. So a decent fraction of these are happening in pretty extreme starbursts, also manifesting in things like a high ionization parameter. And so it's been proposed that perhaps what is driving this host galaxy preference doesn't have to be metallicity, it could also be a preference for just some extreme star formation conditions. And so the authors of this paper actually argue that superluminous supernovae are some of the first stars to explode in a starburst, and take trends like this to mean that this has to be, you know, a preference for extreme star formation conditions is the most important, that they're very young, very massive stars. Now, if this was true, though, you would also expect a local preference for highly star-forming regions. So if we look at resolved data with HST, which we have a small, but we have a sample of, then we can go and look at where inside their galaxies do these superluminous supernovae explode. Are they actually consistent with these most highly star-forming regions? So I'm just showing you some, well, they're not as pretty pictures as HST data usually is, because these are really tiny dwarf galaxies, but you know, these are some examples from the sample. Basically, about half of them look more or less like this. They're compact dwarf galaxies, basically. The typical size of the ones we have HST imaging of is about a kiloparsec half-light radius, so they are tiny and compact. And then about half have some sort of complex morphology. Maybe there's some mergers going on, or at least, you know, irregulars. And looking at where they are in the galaxy, I'm going to build up this diagram because it is a little bit complicated. But what I'm plotting here is the fraction of galaxy light in locations, or really pixels, fainter than where the supernova was. So if it went off on the brightest pixel, that would be a value of 1. And then I'm going to make a distribution. So if you had a population of transients that were just tracking the host galaxy light exactly 1-to-1, they would fall on this diagonal line here. And if you're down in this corner, that means you're more biased towards the brighter pixels, the most strongly star-forming regions, because we're looking in UV light here. Whereas if you were up here, like the short gamma ray bursts Wenfei Feng was telling us about, then you're decorrelated, basically, from the light. And the core collapse supernovae from GOODS more or less follow this line, 1-to-1 line. So their locations are basically where the star formation is. The GRBs, on the other hand, there's this famous result that they are biased towards the brightest regions of their host galaxy. That is, they fall down in this direction on the diagram. They're more likely to explode on top of the brightest star-forming regions in the galaxy, which has been interpreted to say GRBs have higher mass progenitors than just core-collapse supernovae. So where do the superluminous supernovae fall on this plot? The answer is somewhere in the middle. So they are definitely on this side of the diagram. They are biased towards the brighter regions, but at least with the sample size we have, they're certainly not obviously more biased towards the brightest regions than our GRBs, for example. And they are actually fully consistent with just tracing the star formation in their host galaxies. So this is not the result you would expect if the superluminous supernovae were the very first stars to explode in their host galaxies, if they're really the most massive stars. But I mean, I should be honest and also note that this is a small sample. There's only 16 objects here, so I can't statistically say that they're different from either the GRBs or just a core collapse or one-to-one line. And the way to fix this is obviously to get more HST data, which we should do. So there is this really unresolved question of what drives this host galaxy preference for the type 1s. Is it mainly a metallicity effect, or is it an extreme star formation effect? And I really like this figure from Dan Perlis' paper, trying to get at this by basically plotting the competing variables against each other. So this is now the PTF sample, a pretty low redshift sample that we have plotted here, and on the y-axis is oxygen metallicity, and on the x-axis is specific star formation rate. And what you see basically is that below a certain metallicity, the type 1 superluminous supernovae are consistent with this star-forming galaxy population at those metallicities. So below a certain threshold, they just follow where the star-forming galaxies are. Whereas you see you have a couple of higher metallicity outliers, but the rate at these metallicities has to be suppressed, basically. On the other hand, if you look in this direction, you see a wide range of specific star formation rates. So, there are a couple of local volume galaxies out here as well, because once a dwarf galaxy goes starburst, it really goes starbursts. And there are examples of galaxies like that. But by and large, you see a much bigger spread in specific star formation rates. So this would indicate, I would argue, that probably metallicity is a more important factor than extreme star formation conditions. And if you go read Dan's paper or look at his poster, which I highly encourage you to do, he is arguing that basically below about half solar metallicity, superluminous supernovae do not seem to show any particular host galaxy preference, but above that metallicity, the rate is suppressed. I briefly wanted to mention that there are some intriguing similarities and also differences between superluminous type 1 supernovae and long gamma ray bursts. They both are stripped, very energetic explosions. They've both been suggested to have central engines. They're both generally found in kind of dwarfy little galaxies. Perhaps there's a metallicity-dependent rate, etc. However, myself and many other people in this room, I suspect, get to spend next week discussing this at a meeting at Space Telescope. So I'm not going to go into this in any more detail, but I do look forward to that. So finally, I should mention type 2 superluminous supernovae. So this is again from Dan's paper, because the biggest type 2 sample by far is from PTF at the moment. So those are the red points on this plot. And as you can see, unlike all of these blue points which are the type 1 host galaxies, you find type 2s over a much wider range of galaxy types, basically. There are some in extremely faint galaxies. In fact, the two most extreme galaxies in Dan's sample are type 2 superluminous supernovae, but by and large, they seem to more or less follow the star-forming population. There's no obvious preference for low-mass, low-metallicity galaxies in the same way that there is for type 1s. And that is probably telling us that these two populations have different progenitors, basically. So that's interesting. Here we're seeing star formation rate versus stellar mass. You could also look at a mass metallicity diagram, and you get a similar result, basically. So, the blue points in general live at low metallicity, the red points you find over the whole range. I finally just want to mention that there are now 2 examples of type 2 superluminous supernovae that you find in pretty unusual environments. So the first example is this supernova 2006 GY, which is in a massive early type galaxy, although later data suggested there is some star formation there. So, it's still consistent with coming from a massive star. But it is generally very different from the bulk of galaxies that you find superluminous supernovae in. And there is now a second example of a host environment like this from PTF as well, this 10 TBZ. So whether this is a different progenitor channel, we could speculate. They're certainly set apart from the entire bulk of other superluminous supernova host galaxies. And in this context, it is perhaps also relevant to mention Assassin 15LH, which is claimed to be the most luminous, superluminous supernova ever. That is a type 1, so at least if you're going from host galaxy properties, it would be many sigma away from the entire rest of the population of superluminous supernova host galaxies, because Assassin 15LH is also in one of these red, not obviously star-forming galaxies, and coincident with the nucleus, which has made some people suggest maybe it's a TDE and not actually a superluminous supernova. I can let Ben comment on that later, perhaps. But certainly from the galaxy perspective, it is very, very, very different from any other superluminous supernova type 1 host galaxy. And yeah, that is basically what I wanted to say. So superluminous type 1 supernovae show a very strong statistically significant preference for dwarf galaxy hosts with low masses, low metallicities, and a high fraction of these starbursting dwarf galaxies. We can argue back and forth whether this is due to a metallicity-dependent rate or some special star formation conditions or both. Whereas type 2 superluminous supernovae are found in much less extreme environments and come from a wide range, from dwarf galaxies to massive galaxies, generally following the star-forming population. Thank you.
So, Ragnhild, you mentioned Peter Blanchard's paper on the GRB locations. I think the important result from that paper that I'm not sure has been fully absorbed is that this entire preference that was found in Andy Fruchter's result for bright UV environments is not driven by some random distribution of these GRBs around star formation in the host galaxies. It purely comes from the fact that a large fraction of GRBs are happening in the central regions of their host galaxies. And it's really just can be recast as a preference for GRBs to occur within about half of a half-light radius of the centers of their galaxies, much more so than core collapse supernovae or what you would expect for any stellar population. So I think there's something going on there where there's a combination of metallicity selecting which galaxies these events happen in, and then there is something else going on that says that they're more common in the central parts of those galaxies. So I think it will be interesting to see how this develops for the superluminous supernovae as well. But I think we should be open to the idea that there could be multiple effects in reducing the fraction of progenitors that produce these systems. Yeah.
Ragnhild, you said that you could comment on 15LH being potentially a TDE, so could you comment on 15LH potentially being a TDE?
Well, I mean, I'm just saying that it is very blue, UV bright, does not actually look like any superluminous supernova we've seen before, and it's happening in the nucleus of a red galaxy. It also does not look like a typical TDE, but, give it, or does it? I don't know. No. But, in terms of, there are, sure, so you have two different very blue transients. It looks like a typical host galaxy of one and not like the other. So from that perspective, it's more likely to be a TDE, I would say.
it doesn't look like the typical host galaxy of a TDE. The galaxy is too big, so most likely the black hole is too big, and then you wouldn't expect any TDEs whatsoever. So
Yeah.
it's
a very interesting.
It looks different from both classes.
Fair.
So very nice work. I had a question. So using some of the analogies, as you mentioned, for GRB hosts and applying them to superluminous supernova hosts, one thing we found for the GRB hosts is that, and I was led by Pat Kelly, is that the host galaxies are compact, but they're even more compact for their mass compared to other field galaxies. And so that's where we said, well, perhaps there's a secondary factor, not just low metallicity for GRBs, but also this kind of, in addition, dense, perhaps, super cluster kind of environments. So I was curious, since you have these nice data set with HST data of the sizes of those galaxies, have you done some similar analysis? And if so, please remind me.
Oh, yeah. So we did look into that as well. So in general, the superluminous supernova host galaxies are even smaller than the GRB host galaxies. But if you look at things like the star formation rate density, they fall in a similar region as the GRB host galaxies. So they're also overdense, basically, compared to similar mass galaxies. They fall in a similar region in that diagram.
All right, one last question. Yeah, perhaps a naive one. The assassin object is so unusual. I'll grant you that we haven't seen something like it before. You say it's blue, people do, and they say it's also 10 to the 44, 45 ergs per second. That's really hard to do without having hydrogen around, I'll tell you as a model builder. Could it be with that enormous luminosity of blue light that it's ionized all the hydrogen to some great distance around itself, and actually there's a lot of hydrogen there?
That is probably more of a modeler's question, but I imagine that if that is true, then eventually, as it expands and cools, you should see the hydrogen. So to find the answer to that, we should just keep monitoring it, I guess, and see if it eventually shows up.